Can you hear me? I believe the broadcast is on right now, live. Yes. Okay. Welcome to weekly webinar number 8. For some reason, I'm not able to see myself on the screen. Okay, what I am going to do is try to. Let me see what I can do. I hope it's playing right now. I see the volume going up and down, so I'm assuming that everything is all right. Um, okay. And it says the broadcast is live. Let me try something. Okay. I think everything's all right. Can everybody hear me? Welcome to weekly webinar number 8. My name is Michael Floyd. I am your mentor and your mentee. You learn as much from me as I learn from you. So now, same things, meeting with me to fill out your introduction form still. Last week, 5 out of 14 have not completed. This week, 5 out of 14 have not completed. It's something that I am very, very scared of is that still 8 out of 14 of you have not completed your first project. We are in a state of emergency. Those people need to contact me as soon as possible. I keep sending emails every week, and hopefully somebody gets it and responds to the emails. Like I said, the money's already spent. Let's hurry up and try to get this thing done. 30 minutes in the morning, 30 minutes at night. And every time you spend time, just finish by writing it on Slack so the group knows that you are spending time and that you've completed lessons, right? Make it kind of a cooperative spirit. I hope to see more participation in the Slack channel. Like I say before, in every webinar, the cases of 3 students, right? You have student A who has no responsibilities. All it's do is get this thing done, right? We are all not student A. You have student B and C. They both have jobs and children, but student C stays consistent with his schedule, while student B makes everybody else pay the price while he makes sure he gets his work done. All right? Be more like student B than student C. Okay, now this webinar, we are going to be looking at different training techniques for when you are training your neural network. I know it can be a challenge to get the network trained and making correct inferences. We already went through the previous webinar on using PyTorch and also transferring and beginning the introduction to the second project. So all we do now is just think of some techniques and that are better used in order to optimize this neural network. All right. With that being said, I will share my screen and we will get everything going. I'm waiting for this thing to pop up. Excuse me. It's taking a while. I'm not sure why. Okay. Okay, is it shared? Then it's not popping up at the bottom. Okay, all right, we got it. So the screen is shared. All right. The first thing I want to show you is I'm going to actually be going through 4 different projects that I did through my nano degrees on training neural networks, and in those different projects, I use different techniques, and those techniques are highlighted through those different projects. And so I hope to share with you 10 different things that could potentially help you, and definitely will help you train your network to get better accuracy and performance. So this is actually the semantic segmentation project. And what that does is it's for each pixel in the graph, uh, it will then output, what on what exactly you trained on and what the pixel represents. So, in this project, I actually use it to, detect the road lanes as opposed to the things on the outside of the road. So, of course, detecting where the road is definitely important for a self-driving car to drive. And that's what this was actually for. This is actually one of the last neural network projects that I did in Udacity self-driving car narrow degree. So, I use TensorFlow for this, and the GPU on Amazon Web Services. But so, just starting off, what we have is we have the loading the graph. We actually use the VGG 16 in this case, and after we load the graph, similar to what you've seen in the learning from PyTorch, and how you have names to the potential parts of the graph that you want to change. What I did is I got those parts out of the graph because I will be using it to change the network when I am training. And this is the actual part that I need to use to train. So from here, what you have is you have W0. So I need to know what the input needed to be as far as in this graph, right? So you have to know the dimensions of the input, dimensions of your picture in order to change, or in order to input your picture into the graph. So that's what W0 is the initial image input, right? What dimensions are your first image? The keep is the dropout. So the dropout tensor needs to change, right? When you get into accuracy, you don't want to drop out anything. But when you are training the network, using dropout is a very good idea. It helps to protect the model from overfitting by relying too heavily on one part or perhaps one node to derive the prediction or the inference. And we have W3 and W4 and W7, which are, by layers. W3 happens, and then W4, and then, two layers down, W7 occurs in the model. And what we do with these two layers actually is, so we produce a one by one convolution, which just, doing that will help you determine, exactly how important the tensors are in the output. But what we do is we're actually upsampling in this example. So, the previous, as far as W3 and W4, that information from those features that are not as refined as information from the 7. We want to incorporate the 4 and the 3 into the information from the 7, which is really refined. So what we are doing is we are taking, you know, non-refined information, and then upsampling so that, now the 4, now the 7 is the same size as the 4, so it can be combined. And then we upsample the 4 and 7. Now the 4 and 7 combined with the 3, then we upsample that to then keep training. So that is what I wanted to actually, those things what I want to show you is, you can use non-refined parts in your layers to train your network. And also what you have here is you have your L2 regularizer. So I'm using the L2 regularization in this case. L2 regularization is something you've seen in your previous lessons, L1 and L2. Apply different functions to the weights in order to protect weights from becoming too large. And okay. This is the next project. This one was what? Building a traffic sign classifier to recognize different traffic signs. I believe I went over this in one of the previous lessons. So, of course, you're importing the data sets. And the big thing that you take away from here is that the classes, uh, there are 10 classes. But the big thing is that the number of samples from each class are the same, which is important, especially when you're training a neural network for, let's say, if you are trying to train a whole bunch of images that some of them had cancer, some of them did not have cancer. But let's say you had a whole bunch of examples with no cancer and very few examples with cancer. That can be a problem. So what you want to do is you want to, in your loss function, either train your loss function to um, penalize higher when you get something with cancer wrong. You can also undersample the ones without cancer, so you have equal number. And you can also augment the data. So when you augment the data, let's say flipping it, rotating it, different things you can do to augment the data. Just and then you have more images to train on. So whatever you would like to make sure your classes are, either the same or either they represent what you're actually trying to do as far as population. Right. So here the classes are the same. So that is something that is important data augmenting. Okay, and what you see here is you have a mean of 0 and sigma of zero point 0.1. And what I use those for is to create the weights. So whenever you begin training and you have weights that you're beginning to train, you do not want to start these weights at initially 0. Right? What you want to do is, I'm taking a random sample with mean 0 and standard deviation 1 from a normal distribution. So that's what this is about. It's taking different weights from a normal distribution, so they don't start off exactly 0, but they start off small enough because you remember you want to add those regularization penalties. You do not want weights that are too big, right? So never start off your weights at exactly 0. Okay. So this next project I will want to show you the behavior cloning project. So what I did in this project is I used a whole bunch of images that I took from driving around a racetrack simulator. And from those images, I was able to then trained a neural network to drive the car based on where the car is and drive the car around the racetrack. So it's pretty cool. I'll show you in the code. So here's the code. I use Keras for this one. And what I wanted to show you on this one is, okay, Blue Lambda, right? So you must make sure the inputs are normalized. So you have 3 dimensions. It's usually 0 to 255 as far as red, green, blue. It's subtracting 128, which is the middle between 255 and divided by 128. So you're normalizing everything's between 0 and 1 now, or 0 and yeah, everything between 0 and 1 now. So that is so actually it's between -1 and 1, because if it's 0, then -120 divided by 255. So everything's between -1 and 1 in this example. This is how it was normalized in this case. But of course, you can normalize it from 0 to 1, -1 to 1. Just maybe depends on what you are doing. And we have here an example of Keras when you're starting out convolutional 2D max pooling. Then another 2D layer, and all the way until we flatten it out when we have dropout in this case as well. And then we have all these layers until finally we have a layer right here. And the number of epochs is 4. And remember, when you are training your network, what you want to do, what I usually do is I set the number of epochs to, let's say, 30 or so. So I could see exactly when the training stops. So what's going to happen when you set your epochs at 30? The training is going to keep going as far as increasing in accuracy. But what you will see is you will begin to see a drop of some sort as far as validation. Validation, you will stop beginning to see your accuracy grow with your validation. And once you see accuracy quit growing in your validation, then you know that you need to stop your training. So right here, you stop your training right here. I usually set it to like 30 or so I can see exactly when. In this case, I stopped at 4. So after running it the first time, seeing exactly where it was as far as I plot the mean squared error loss. I see exactly where it is for the training and validation, and then so I stopped at 4 for this case. And let me see, documents. Submission materials. This is just from when I submitted the model. So the goal was, to use this neural network in order to be able to steer a car around the track. I just wanted to show you how the final output was. And one thing that really helped me in this was exactly the images that I was putting into the model. So, that is another thing as well. It's the garbage in, garbage out, right? What you want your model to predict correctly, it will, as long as you put the right things in order to predict the model. So one thing that was a problem in my case was that it was running off the road. So what I had to do was I had to, make examples where if it's going too far to the right or too far to the left, input images that show it what to do when it's moving, right? So now it knows when it's going too far to the right, I gotta push back, right? So I inputted images, so now it knows to push back when it's moving too far to the right or to the left. And these two curves right here are what gave a model a lot of trouble as well. What I did in order to get through to these curves is I also, instead of driving um, in one direction. I reversed and drove in the opposite direction. So I guess it helped train the model in the right direction, the opposite direction. But by driving in the opposite direction and putting images that were driven in the other direction as well, it better helped train the model. Uh, Maybe it's due just the lanes being the yellow being on one part of the lane and whatnot. But it's another way, a technique to augment the data pretty much. So when I was just driving and continuously driving, right, those images did not work. But when I started, to help my model by, whatever it did not do well, putting in things that needed, right? So whether that's maybe more of one particular class or whatever is the problem with the model, just make sure what's the problem. You could sometimes analyze that and make sure that it is doing or making inferences correctly. So that's just one example, the garbage in, garbage out thing. Normalize inputs, so I believe everything. Okay, and stop training with no validation. So, and this last one is for vehicle detection and tracking. And what I did for this one is, okay, you have a car driving, and the purpose of it is to detect other cars, other vehicles, just based on the images that were provided. So of course you train your network to detect what's a car, what's not a car. This is the code for that. Actually, let me just go back. This back. So. I believe this is the code. So, this is the network I used. All right, so you input the images. This is the network that I use. Keras was used for this one as well. See the normalization, the input shape, activation layers, and the last layer, sigmoid, categorical trust attribute. Epochs for this one was 3. So, so this is just looking at the loss, right? So this is just, before, of course, I most likely had an epochs, 15, 30, and saw exactly when, as far as the training stops. So this is first, second, and third. Of course, it begins at 0, 1, but, I'm just trying to make sure for myself it's training well. So, I mean, that's epochs are set to 3. That is the model that detects where the images is, where the images are not. But the thing about and what we did is slid a window across the image, and sliding the window with different sizes detected, where the car is. But even with that window sliding, what I tended to see was I'm not sure where the previous code just went. I'm looking for. Hold on 1 second.
I should have opened that back door. No, I should have opened that back.
Yes. Okay. So, one thing I found, even with the sliding the window, is that it's sometimes the text where the picture is, sometimes it's not. So what I did in this case is I used information from previous seconds to determine, so if it saw, a car on one part of the frame for the previous 5 seconds, but for some reason not detected for that second, we override with the information from the previous 5 seconds. So that's something that I used just to help. I believe it was an image. It wasn't 5 seconds. Remember, it goes every. I guess you probably have maybe probably 50 or so images per second, if even that small. So maybe probably the previous like 10 milliseconds or so, getting those 5 or so images, and also the previous 20 milliseconds or so, just doing a bag thing in order to make sure just the initial inference is not kind of thrown out of whack, and making sure that using information from previous inferences as well, and that is something that is important. So not only using those inferences, but you can also incorporate different models as well. So, in one case, if you do not have the opportunity to use something of a time series nature similar to what I did, what you can do is train different models, right? So, train different models in order to, uh, we'll train different models. So use information from different models, kind of like a random forest technique you'd be having. So now you have, 3 or 4 different neural networks, and possibly a VGG13 and a fully connected 8, maybe a Linnet architecture, right? Different architectures, and through those different architectures, after you train the models, uh, then using those models and based on a uh, probability from those models, then um, determining exactly what this is, right? So, okay, here it is. I couldn't see the bottom of the screen for a second. So, with that being said, that was a quick one, I guess, right? I believe we've covered the 10 things that I wanted to drop as importance, right? So, information gained from previous layers, possibly the less refined layers can tell you things that the more refined layers do not. Use the L1, L2 regularization penalties, dropout. All classes are trained the model with the same volume or weight attributed to each class, right? So if you don't have enough classes in one, you all make the data, oversample one class, undersample the class that's overrepresented. Those things. So when initial, make sure the weights are also not initiated with 0. A random uh, normal sample mean 0 around, standard deviation 0.1 is fine enough, right? You will also want to make sure the weights are not initialized with a high value, right? Because you do have the regularization penalties. Garbage in, garbage out, right? Make sure you are putting in what you want to detect, and if there are problems, you can adjust your input for your images and what you are training with. But it's not images, right? It could be anything, right? So, and normalize your inputs into the model. Stop training when no improvement arises for your validation. No need to rely on just one neural network, right? You have a whole bunch of different architectures that you can easily use and easily train and do a little couple adjustments with transfer learning. It's quick with a GPU almost if you just follow the previous 8 or so steps, right? So just transfer learning, you have a whole bunch of architectures to give you a whole bunch of inference instead of just one inference to rely on. And transfer learning, okay, of course, like I said, right, you have the architectures that you have seen from your lessons, and all those architectures used instead of just doing it yourself and doing instead of doing it yourself and creating your own architecture. Those architectures have been proven to work. All right. With that being said, I will give 5 minutes for any potential questions. So the last one was transfer learning. Of course, you already know about transfer learning from the last one. So those are the 10 things, 10 tools. So with that being said, I will leave 5 minutes for any questions. I'll be looking at the group chat. And if I do not see it on the group chat, you can also put it on Slack. I'll be looking at the Slack channel right now to see exactly if anybody is messaging me on the Slack channel as far as any questions they would have for any questions about training and networks, any questions about the second project, or questions about the first project. All right, we have 3 more minutes for anybody to ask any questions. Feel free to ask questions. And what I want you to do for next week is finish the project. So that is what we are working on next week, is finishing the project. You should have started last week. This week, I hope we can finish the project. And if not this week, then next week. And I hope everybody who has not finished the first project can complete the first project. it another minute. All right. No questions. I don't see any. With that being said, I guess I will end the weekly webinar number 8. Like I said, I would like you to do is like to complete the second project. For those that have completed the second project, please complete the first project. All right, and let me know how everything goes. All right, peace.